עשה את המאסטר פה בתל אביב עם עודד רגב, עשה את הדוקטורט בירושלים עם דורית אהרונוב, ואחרי זה עשה פוסט-דוק ב-MIT. יש לה עבודות מאוד יפות על ה-Local Hamiltonian Problem, על ה-Quantum PCT Conjecture, על Small Space Quantum Algorithms, ויש לנו גם עבודות מאוד יפות שמתרגמות רעיונות שנעשו בעולם הקוונטי לעולם הקלאסי. למשל, בשביל למצוא את הערכים עצמיים ופקטורים עצמיים של מטריצה, למצוא במקדים, זה אלגוריתם שלוקח רעיונות קוונטיים והופך אותם לאלגוריתם קלאסי לגמרי, או עבודות שהיו לאחרונה על טירוף של הפרמננטה. ועכשיו נשמע את זה.
Switch to English? Okay. Okay. So, hi everyone. Thanks for coming to the talk. This difficult hour. Okay, so this talk is titled A Quest for Robust Quantum Entanglement. And then maybe later throughout the talk, I'll shift gears into the classical world. Okay, so first of all, what is entanglement? Okay, entanglement is a phenomenon by which faraway particles are coupled, possibly in ways that transcend classical correlation. So you can devise experiments that would behave differently with quantum entanglement than they would with any classical correlations. So take Schrödinger's cat, right? Its popular image, which is this one, right? Half dead, half alive, or 1 over square root 2. So this is only really half the picture, because in reality, the cat is entangled, we say, with a poison vial. If the poison vial breaks, it's dead. If it doesn't break, it's alive. So you can ask about, what about robust entanglement? So entanglement is the source of quantum speedup. So we know that if we want, for example, to factor integers in time which is exponentially faster than what we can do classically, then we need a quantum state that harbors that computation to be highly entangled. However, physics has its way that entanglement tends to dissipate very quickly. And so, if we want to build a quantum computer, we must retain it. This is called the coherence time. So anytime you buy a quantum computer on Amazon, you better check that coherence time is pretty large. Today, the coherence time is not long enough to sustain deep enough quantum computation to get us to solve interesting problems. So, in comes Dorit Aronov and Michael Benor. They have the fault tolerance theorem that says, well, even if you have a constant fraction of random errors, you can correct them by imposing quantum error correcting techniques. The point is, what happens if your coherence time of the quantum states ends even before you can apply that active error correction? Well, in that case, you get nothing. Game is over. The system would dissipate into classical correlations. You wouldn't be able to even invoke your very sophisticated quantum error correcting scheme. So what we want is entanglement that somehow can sustain itself, right? Kind of a quantum memory. So you devise your quantum setup, your quantum Hamiltonian, and you let it sit out there in the sun, not at 0 temperature, at some modestly low temperature, and you require it to kind of retain its long-range entanglement for a long time. Okay, so let's start with some definitions. So let's talk about entanglement as a mathematical property, right? So in quantum, we also always talk about a Hilbert space, which kind of abstracts away whatever we have below, like electrons or photons. It doesn't matter. At the end, it's a complex vector space, which is associated with physical qubits. So we usually write this is a complex plane tensored to the nth power, where n is the number of qubits. And a quantum state is just a unit vector in that space. And you can write a tensor product state. A tensor product state is something which is completely unentangled. It's just particles that sit beside each other, and they have no correlation between them. So this is a tensor product state. So one may be tempted to say, well, okay, whenever I cannot write a state in this way, it is entangled. It's a valid definition. However, it's neither robust nor useful, right? If something is very close to being that state, it's not really entangled. And I will show later a definition which is even more interesting. Okay. Essentially, the most important property of a useful definition of entanglement is that it should behave like physical reality. In other words, it should be local. So we want quantum states with nice properties. And quantum states are actually meaningless without context. So this is not an abstract mathematical object. It's not just a vector that sits in high-dimensional space and can do whatever it wants. It has constraints. So the context of quantum states are physically realizable systems. These are local Hamiltonians. So physically realizable systems you can think of maybe as a set of magnetic fields that each of them acts locally on, say, triplets of qubits. And you can do this arbitrarily on any subset you want. And in the physical world, we cannot do any operation on the qubits. We can only do things which are local. So for example, to impose a magnetic field on subsets of qubits, this is something which is allowed. So these are called local Hamiltonians. Mathematically, these are just a set of local positive semi-definite matrices. I'll talk about that later. So any physical quantum state is actually something that sits in the linear span or convex mixture of eigenstates of such operators. Right? You cannot reach, not all unit vectors are interesting. In fact, almost all of them are not. Those that are interesting are those that you can somehow relate to an interesting a linear span of eigenstates of something that arises from a locally defined quantum system. So the amount of entanglement that we'll see in a state should relate to how hard it is to generate it using a local quantum circuit. So what is a local quantum circuit? It's something that looks like this. So you have d layers of a circuit. This is very, very much like classical theory. And these qubits are coming in. These are the wires. And at each layer, you can kind of partition the qubits into pairs and then apply a local unitary operation on each of them. Maybe the next layer you can kind of permute them and do a different partition and so on. At the end, you get d layers, and you should have somewhat of an entangled state up here. So notably that each of these operators acts in tensor product. So these are tensor product of unitary operators. If you're a physicist, you would say, well, you cannot really invoke a unitary operator. You can invoke like a magnetic field, and then the unitary operator would arise from the solution of the Schrödinger equation. Okay, so these are a bunch of Schrödinger equation solutions that arise from that magnetic field. And in computer science, we model them as just applying tensor product unitary. Okay, so let's try again. Let's define a quantum entanglement using quantum circuits. So let's define a quantum circuit lower bound. So for any state rho, the circuit lower bound for rho, or C of rho, is the minimal integer d for which there exists a unitary circuit, u, such that if it acts on the all-zero state, or something which is completely unentangled, and maybe you can toss away some of the qubits later on, you can approximate rho to arbitrarily small trace distance. Okay, so this is maybe a mouthful, so let's look at this for a bit. Again, you start off with unentangled states, and I allow you to invoke a depth d circuit, and then maybe throw away some of the qubits that you end up with, and at the end, you should be able to approximate your quantum state to arbitrary precision. Okay? Again, this rho here does not need to be a pure state. It could be a random ensemble of quantum states, but you still need to approximate it to total variation distance. This is what it says, really.
What is D of U?
The what?
D of U?
D of U is the depth, the circuit depth of unitary U. This is like the D that we've seen before. Questions? Okay. Okay. Yep.
The circuit is on the local gate.
Yes, exactly. This is the fact that it's tensored on pairs. So let's test our definition. So for any tensor product state, the depth complexity is just 1. We do nothing. Right? Actually, a quantum state that is very close to a tensor product state also has circuit complexity of 1. Does do nothing. You still get an approximation error that you can use. Well, it depends on, up to that, right. But we can also show, and we'll do this later, that a quantum state that belongs to an error-correcting code, a quantum error-correcting code of n qubits, which has a linear minimal distance, has a circuit lower bound which is logarithmic. So if you have a quantum error-correcting code, that quantum state, you need a depth d circuit, which is omega log n, because essentially you need to be able to couple any pair of qubits. So this is what it means, really. Okay. So let's define a bit what does it mean to have a local Hamiltonian. So a local Hamiltonian is a positive semi-definite matrix, which can be written as the sum of other PSD matrices, where each one acts on only a small, very small subset of the qubits. So it's identity on most of the system, almost all of it, and maybe it's a PSD operator on an 8x8 matrix, like on 3 qubits. Okay, this is a local Hamiltonian. Actually, if you're from TCS, you've probably already seen it. This is like a CNF formula, right? So we all know what CNF formulas are. Think of a disjunction, which looks like this. So x1 or not x2 or not x3. There's a corresponding Hamiltonian term to which penalizes those qubits if they are in the only state for which this disjunction evaluates to false. So this would be a projection onto the state where the first, second, and third qubits are 0, 1, 1. Okay? So if you have a disjunction like this, you can write a PSD term for this. It's a projection operator. So essentially, you can Hamiltonianize a conjunction of such disjunctions. So you have a CNF formula. You can write a local Hamiltonian that corresponds to that formula, right? Such that the satisfying space goes exactly to the quantum world. And because of this correspondence, you can actually write a Hamiltonian version of Cook-Levin's theorem. So determining whether a local Hamiltonian is satisfiable, just like reset is NP hard. So this is the local Hamiltonian problem is quantum NP hard. This is a famous result by Kitaev. So it's important to keep in mind that essentially when we talk about local Hamiltonians and quantum states, you can really think of this as a quantum generalization of binary satisfaction problem. Yes.
And that to mean that either there is an eigenvector with eigenvalue 0.
Yes, exactly. Yes. You need to have a promise, 1 over poly of the system size. Yes. You need to add an extra promise, which does not exist in the classical world, just so things do not become exponentially small. But this is a side note. Yeah. So our mission, should we choose to accept it, is to show circuit lower bounds for known local physical systems, and maybe show robust circuit lower bounds for possibly new physical systems. And the big question, which for me maybe is one of the more interesting ones, is C of rho a stable quantity in nature? Right, so this is like a kind of a big question, right? So someone gives you a quantum state which arises from a local Hamiltonian, and it has has a wonderful circuit complexity. Maybe you can use it to factor integers. But the question is, what happens if you just perturb the state a bit? Does the circuit complexity collapse very quickly? Right? My goal would be to say, yeah, I can design a local Hamiltonian system such that not only the ground state has a large C of rho, but also small perturbations thereof are stable. In other words, this would kind of defeat the common physical intuition that entanglement is not stable. This is kind of a TCS formulation of that intuition.
Okay. Wouldn't that lower bound then be more difficult than for classical circuits?
It would be different. Yes, I'm going to talk about that. Yes, it's a different set of techniques, right?
No, but I mean, we know that proving log and lower bounds, it's on the one end trivial, and the other end you don't do better.
Right.
So
yes, you'll see arguments which may, they come in different flavors. There's going to be like an information theoretic argument, which gives the log and bound probably not better. And there will be other arguments that you may use to get better bounds. I mean, but there's going to be later on at the top. And kind of a TCS flavor of this question is, can we use this quantity of circuit depth complexity to argue hardness of approximation in computational problems? And we'll see that later on too. Okay. So let's talk about the state of things. Okay. So what questions can we ask? So there are a few questions. I'm going to just write them down and then deep dive into each of them. Quantum PCP, which posits the QMA hardness of approximating the lowest energy state of a local Hamiltonian. Right? So PCP is whether NP hardness remains under approximation, and this is the QMA hardness, whether it's stable under approximation. There is quantum LTC. Are there quantum error correcting codes which are locally testable? Can we test the distance from a code space of a given quantum state? We don't know that yet either. There is the no low energy trivial states conjecture, which asks whether there exist local Hamiltonians with no low energy trivial states. So in other words, if you go deep down into the cool side of the Hamiltonian, you cannot find any kind of easily approximable states. You can talk about NLETS, which are local Hamiltonians where states that look like a code state, like a ground state on most qubits, are entangled as a code state on all qubits. This is NLETS. And you can talk about distributional versions. So this is just kind of the list of conjectures. We're going to deep dive into each of them. So essentially, they all amount to kind of robust entanglement zoo that we'll try to kind of eventually populate. So right now, there's like a lot of empty cages in there, but we still charge tickets at the entrance. Okay, so quantum PCP. So just as the three-local Hamiltonian problem is quantum NP hard or QMA hard. This was Kitaev, right? So the PCP theorem says that there exist CNA formulas that are NP hard to approximate to some constant fraction. So that's classical PCP. So there's the quantum PCP conjecture by Dorit, Arad, and Vidic that there exist local Hamiltonians for which it is QMA hard to approximate the lowest eigenstate to a constant fraction of the operator norm. Right? So this is the quantum PCP conjecture. It is wide open. There has been some progress on adjacent questions, but as far as we know, like there is no favorable direction at this point.
So what do we know? Do we know a polynomial approximation? What is the
I guess it depends on the topology of the Hamiltonian. For example, like if it's a regular grid, then you can definitely have a constant factor approximation. I don't know. Otherwise, if it's arbitrary, I'm not sure if there is one.
So, even polynomial in the number of qubits?
Like polynomial error?
Yeah.
Oh yeah, I guess I guess that would work. Yeah, I guess yes. Right. No. I don't think it's. I mean, I would say that polynomial factor approximation would be possible. But as soon as you talk about constants or the regime of interest in the classical PCP domain, then nothing is known. So I plot down quantum PCP right here. This is in a world where quantum PCP holds. Okay. So let's talk about NLTS. So since there was a lot of time where we couldn't make any progress on quantum PCP, right? So this is a big question. Then people ask, maybe we can ask an easier one. So here's an easier question. Do there exist an infinite family of local Hamiltonians such that any family of quantum states with energy at most an epsilon fraction with respect to their norm have a circuit lower bound of omega 1? So this is easier in a sense because we're not arguing anything computational, right? We're not saying that this is QMA hard or anything. We're just saying, at least be able to show a circuit lower bound. Here's another way to look at NLTS. In general, zero eigenstates of local Hamiltonians can have, say, quantum code states. But other eigenstates can also have high entanglement. In fact, for quantum code states, every precise eigenstate has the same entanglement structure as the ground state. But how about the linear span of all eigenstates? Well, there you can reach any state. So there are obviously trivial states in that linear span. So NLTS asks whether there exist trivial states that are approximately spanned by low energy states. So if I plot this here, think of this as the spectrum of the Hamiltonian. This is the cool side. This is the warm side. The ground state is right here down at the bottom. And NLTS asks, how far can I raise the bar before I get states which are just tensor products? So you're allowed to take a linear span of everything at the bottom here, all the blues. And I ask how far can you raise the bar before these states appear in the span? But like if I go all the way up, I can do any state, right? That's easy, right? This is just the space, right? NLTS asks, how far can I raise the bar? Say, can I raise it to a constant fraction of this operator norm before these states appear?
So when you say trivial state, do you mean a state with a long depth?
Yes, proximable by a low depth circuit.
It seems somehow reminiscent of matrix rigidity, right? Where you want to put some vectors far from span of other vectors.
Yes, I was asked that question. So I think.
You don't know how to prove such results, right?
Right. So I think that it's known that for random matrices, eigenstates are like uniform.
Random everything is easy. Here, probably.
I think it's a different notion because you actually want a circuit lower bound. So you want to be able to apply any quantum state, which is a tensor product of local unitaries and a sequence of those, and you want to show that the number of layers of such a circuit is at least something. So I think it has a somewhat different flavor. I guess, if you just look at a random, eigenvector of a random matrix, it would probably be kind of well spread. But this doesn't mean that it has a high depth complexity. For example, if you start off with the all zero state and apply just a single layer of Hadamard gates, you will get a uniform superposition. But the second complexity is 1 or 0, or or 2 or something. It's very like it's O of 1, right? Okay, so it's counterintuitive, right? Like being like well spread does not mean having a high entanglement complexity. It's okay. So in this kind of picture, if quantum PCP holds, then NLTS holds, right? Because if NLTS doesn't hold, it means that like every Hamiltonian, I would be able to have like a low depth circuit that approximates it, and in a way, I can use that description of shallow circuit to actually give me a witness, a classical witness, to verify the existence of a low energy state, and that would mean it's not quantum. Okay, it's assuming in the back separation between MA and QMA, but I'm up to that. Okay, let's talk about quantum locally testable codes, which we already put up there. So what are quantum locally testable codes? So in classical coding theory, a locally testable code is an error-correcting code, which is LDPC, so it can be enforced by a set of local constraints, but it has an extra property that a random check is violated with probability that is proportional to the distance of the word from the code space. This is being locally testable. These are some examples. We know that classically we can get almost the same parameters for LTCs as we can get for LDPCs. So in some sense, we can buy this property with almost no payment in the sense of rate to distance. Like it's, it wouldn't be random. You would have to work hard, but you can do it. Quantumly, so this is a conjecture by Dorit and myself. There exists quantum locally testable code. So you need to say what the analogy is. So from classical code, you go to a subspace of a Hilbert space. Instead of check terms, you write local projections. And for the third property, the soundness, you ask that the average energy penalty experienced by a quantum state is proportional to the distance, to its distance from the code space. So distance from the code space is actually a Hamming distance. So it's the minimal weight of a Pauli operator such that if you apply to the state, it has a non-zero overlap with the code space. So this is the soundness. So this is an open question. We don't know what the interaction is between quantum PCP and QLTC is. If classical theory has any bearing on this, there would be some interaction. But at least we know, I'm going to show this later, that if QLTC holds and NLTS holds, so we can plot both the intersection here and everything else inside NLTS. Okay, let's talk about NLETS. So let's define an imposter state. An imposter state for a local Hamiltonian H is a state that looks like a ground state on most qubits, say 0.99. So it looks like a ground state on most qubits. NLETS means that you have a local Hamiltonian such that any imposter state is highly entangled for some constant C. So in other words, you have a local Hamiltonian, and someone hands you a state, and you examine it like every 0.99 fraction of the qubits of your choice, and it looks like a valid code state. But you want to know that it is truly entangled on a global scale as it would for a complete code state. And it's, it wasn't known whether this was possible. Maybe you can somehow cheat. So this was my work with Aram, and we showed that there exist local Hamiltonians that are C and LETS for some constant C, which is like 10 to the minus 6, I don't know, something, some number. Okay, so in this zoo, NLETS is here. Okay, so it's in even weaker condition than NLTS, right? Because imposter states are actually low energy states. Because if you look like a ground state on most qubits, and somehow the constraints are kind of regular, they have a regular degree, then you would probably violate few checks. So if you cannot make sure that your things that look like imposter states are highly entangled, then you probably can't assure that low energy states are highly entangled. In particular, quantum PCP is false. Okay. So this one, thermal NLTS, you're probably also pretty tired from all these definitions. This is a recent conjecture. It talks about what physicists are really interested in. What I showed you until now is kind of saying it's like a TCS worst case language. There exists a state such that and so on. But really, when you encounter a physical system, what you encounter is a distribution, usually a thermal distribution, and this is called the Gibbs state. Gibbs state is an ensemble of quantum state where you sample an eigenstate with probability that is e to the minus its energy up to some proportional factor. So this conjecture says there exists a family of Hamiltonians of n qubits such that the zero eigenstates are highly entangled to some omega log n, but also the thermal Gibbs state, and this is a distribution on quantum states, has a circuit lower bound of omega log n. So this is the conjecture. And this is a recent result which says that you can not solve it, but you can approach it. In other words, there exists a family of log local Hamiltonians of n qubits, and beta, which is not constant, but log log n, meaning that it's almost constant temperature. Like the temperature would be 1 over kt, right? Boltzmann constant. So such that the zero eigenstates are entangled, and also the Gibbs state is entangled. So this means that this is a kind of a fancy construction. It's not a physical system that you would see every day. It's not on a regular grid. It comes from expanders. There's a construction there, but it says that maybe if you are willing to migrate from the physical system that you think of, which are kind of lattice-based and everything is regular, to something which is more TCS-y, like locally testable codes, expanders, and so on, maybe you can get something which is physically non-intuitive, namely that there exists distributions at non-zero temperatures, maybe not constant, but something which does not decay too fast in the system size, such that entanglement is pretty well maintained. So, yep.
So this is an explicit construction.
Yes.
And if I allow non-explicit constructions?
Random?
Yeah.
It's a good question, right?
Actually affect.
So I don't know, like if you take a random local Hamiltonian, if that's what you mean, would it have a robust entanglement? I don't know. I think there's... I'm not sure I've seen any work on this. I heard someone working on the question, but I don't know of any formal results. Could be interesting. I guess a counting argument would be kind of a natural thing to do here. Yeah, I guess... yeah, I guess well, let's see. A random quantum state would definitely have that property. This would be an easy quantum. Yeah. Like if you take just a random quantum state with high probabilities, there's not going to be any local quantum circuit that approaches it. The question is, what if you don't sample the state, you sample the ambient Hamiltonian locally? I don't know what the model is, by the way. You need to think about what does it mean. Like maybe sample. I don't know. Yeah. It's a good question. Okay, so in the robust entanglement zoo, the distributional version is kind of intersecting these sets in a non-trivial way. So let's see the summary of the results. Okay, so there's quantum PCP. There's some negative results on this by Brenda and Harrow and by Dorit and myself. And then we defined QLTCs, and then Hastings defined NLTS. And then the work with Aaron, we show that QLTC under certain parameters implies NLTS. And then Hastings showed that QLTCs exist for some inverse polylog soundness. And then we show that with Harrow that NLETS exists. So at least we know that this cage there is something in it. And then there was a separating example last 2 years ago between this class and this class, meaning they are easy to generate NLETS, things which are imposter robust, which are not NLTS. And this last result is a new result. So overall, you can see that there's some work going on around this. There was somewhat of a significant progress on QLTCs, and I think we have a better understanding of the NLTS conjecture. However, this here is a serious mountain. It comes out of the slides here, and we're still not sure what happens in that domain.
The Hastings result is a construction?
This one? Yeah, exactly. It's a high-dimensional version of the toric code, if you're
Question at the high level.
Yep.
So all this is just understanding the complexity classes in the quantum, or they are useful to, as you said at the beginning, to keep your system stable?
So this yellow thing is actually useful to keep your system stable because this is a distributional version. So this result means that you can have a local Hamiltonian, and you can let it thermalize, meaning you can take it out of the fridge, just let it thermalize to some temperature, which is not too low, right? It doesn't decay inverse polynomially fast with the number of qubits, just 1 over polylog log the number of qubits. such that entanglement you can show a formal circuit lower bound for the entanglement that it retains. Yeah. That said, I'm not sure that the entanglement that you get is a useful entanglement in the sense of integer factoring, but it is some entanglement. Okay.
Now we need an extractor for entanglement.
Right. It would be. Okay. So let's get our hands dirty. Enough of the zoo. Yeah, I guess the easiest place to start would be to talk about quantum circuit lower bounds for quantum code states. So a code state of a quantum error correcting code with minimal distance, which is polynomial in n, say square root n usually, has circuit lower bound, which is log n. So this is the theorem, and here is the proof. This is kind of a folklore result, I would say. So how does this go? So someone hands you a quantum state, and it says like it can be generated from an unentangled state using a depth D circuit. So you want to show that D is pretty large. So how do you do that? You say, okay, suppose I have two orthogonal code states, rho 1 and rho 2. Okay? So by definition, any measurement m that I apply to these states, which has support less than the minimal distance, these states are undistinguishable. So in physics lingo, we write this as the trace of m times rho 1 is equal to the trace of m times rho 2. So suppose someone tells you that he generated rho 1 by applying a unitary u on the all zero state. This is in mixed state notation. And the depth of u is just d. Okay? So let us write a measurement operator which looks like this. It projects on one of these qubits being in state 1, conjugated by that circuit, and sums over these qubit indices. What you get, because u has depth d, this measurement operator has support 2 to the O of d. And because if you take rho 1 and you undo u, you get the all zero state. Then if you look at rho 2 and you undo the u, what you get is some superposition which has some support on something which has the number 1 in that string. And this measurement kind of catches that. So what did I do? I showed you two quantum states which in the normal setting would be undistinguishable, and I've shown you how to separate them by a measurement which is not too large, which is 2 to the O of d. Right? But if you look again at the, at the promise of the code, anything that can separate them has to have support at least, which is polynomial in n. So 2 to the O of d is at least square root n, and d would be omega log n. So this is kind of the basic information theoretic proof. It relies on the fact that no two orthogonal code states are distinguishable, but by measurements which are very, very local. So we kind of, if someone claims a local circuit, we leverage that to argue there is a measurement, local measurement that separates them. Questions? So that was kind of the basic notion. But what if we can correct errors, right? Most states are not, do not belong to any quantum error correcting code. Doesn't mean we should kind of, stigmatize them. Okay. So let's talk about a weaker criterion. Suppose we have a quantum state that is supported on faraway sets, right? So what do I mean by that? Think of a cat state. Cat state, which is, say, with probability half, it is uniform on the Hamming ball of weight at most n over 3, and probability half, it's uniform on strings of weight at least 2 n over 3. Like that, right? Can we show a circuit lower bound to generate that state? Okay. Okay, so this is a technique that we use in our paper from 2017. So let's start the same as we did before. Suppose that you have a state rho 1, which is generated by a depth D circuit, okay, from the all zero state. Now there is no rho 2 here, just rho 1, right? Because it does not belong to a quantum error correcting code. But we know that rho 1 is supported on faraway sets, right? So if you measure it, say, in standard basis or any other tensor product basis, you get some separation. So there exist two sets with large measure that are separated by some polynomial distance, say omega n. Okay, so let's take rho 1 and mess it up a bit. Let's apply on rho 1 a reflection about S. So this means that I apply a minus sign to all states in T. Okay, so I get like S plus T in the first state and S minus T in the second state. Okay? For simplicity, you can assume it's orthogonal to rho 1. And now let's consider the Hamiltonian, which is the same thing that we've seen before. It projects onto one of the strings being, one of the bits being 1 after undoing the action of u and summation over the qubit index. Okay, so it is 2 to the OD local. It has 0 eigenvalue for row 1 and 1 eigenvalue for row 2. But we're not done, right? No one told us that you can't do this, right? So this is a local measurement that distinguishes between the state and its T-flipped version, but no one told us it's illegal, right? So let's see how do we leverage this into a proof. So let's do this measurement on steroids. So we take M as an operator, and we push it into a Chebyshev polynomial of degree square root M. So by doing so, we get two things.
Lior, what is M?
So M is the measurement, this measurement, from before, right? Whether there's a 1 in the qubits. Okay. So now you push M into a degree square root and Chebyshev polynomial, and you get another operator. It's much larger, right? It's not local anymore. It's only 2 to the O of D times square root n local. The good thing is that now the spectral gap between row 1 and row 2 becomes a constant fraction of A. So before, the difference in energy between this state and this state was just 1 over system size. Now it's a constant fraction. So let's do some calculations. What we do is we show by the spectral gap property that the energy of A on row 2 is at least some measure of the measure in S. On the other hand, we know because of A is somewhat local, it's only 2 to the O of D square root n local, that it cannot distinguish sets which are far away. So the energy of A on row 2 is at most the mass that sits on the Lth boundary of S. So you look at all strings that are a distance at most L from S. The energy that A assigns to row 2 is at most whatever is in that boundary. It cannot be larger than that. So once you divide the two, what you get is a cool thing, which is an isoparametric inequality. It's kind of the expansion. So anytime that you have a quantum state which is not too deep, it has a large isoparametric inequality in some tensor product measurement. Okay, so L here is our exponentiated depth times the degree of the Chebyshev. And what we show is, in that case, the distribution is such that if it's only of depth d, there are many, many strings that await you in the Lth boundary of your set S. But since S and T are disjoint and are square root, are distance omega n from each other, then D must be very, very large, right? So this is kind of the corollary of all this. So we've shown an isoparametric inequality on the distribution of circuits with low depth. And if you are handed a state which is like Moses parting the seas, and there are two walls of water which are far away, it must be because there is a large depth circuit that did that state.
So why did the degree n explode?
Oh, cool question. Yeah. So in some sense, Chebyshev is kind of the optimal trade-off, right, between degree and amplification, because if you have two eigenstates, like one is 1 and one is 1 minus 1 over n, if you want to separate them into a constant, you may be tempted to raise to the power n, right? Get 1 and 1 over e. But then your locality would have like n here, and then the argument would be dead, right? Because you cannot have separation better than n. So it's what kind of trade-off, like, what's the minimal price in locality that I need to pay to get a constant spectral gap? And this is the Chebyshev, which you can do no better, right? Because it's Chebyshev. Okay, so let's talk about some structural theorems. So to recap, we've seen a definition for entanglement complexity using a minimal depth circuit. And we have shown a robust entanglement zoo and its interconnects. And most of the physical systems that we are looking for are actually not known. So what should they look like? Maybe if we can find them, at least we can say something about them. So there have been some structural results. For example, so paper with Dorit, any quantum stabilizer code on a 3 hypergraph has a very, very small quantum error correcting distance. Meaning that if your system is too local, it's not good, in a way, at least in that setting. Another maybe surprising result, if you're from TCS, if your bits to constraint graph, if you look at it as a Tanner graph, bipartite graph, if it's too expanding from bits to constraints, like think of a Sipser-Spielmann code, it's not NLTS. You can actually find a classical witness. So it's kind of surprising, right? You would expect that the more the larger the isoparametric inequality, or the more expanding it looks, the more hard it would be to approximate. But this actually goes against that intuition. And a more recent result is the need for structure in quantum codes. If there is a quantum system which is a K-hypergraph, you take K subsets, it's K-uniform hypergraph. If it looks kind of uniform, like epsilon pseudorandom in some definition, then also the distance is very, very small. So something which is too random looking is probably not too good as well.
This is a function, this is constant. The top is constant?
The what? I'm sorry?
Constant, not function, right?
This one?
Yes.
Yeah. Distance is 5. Yeah.
This is a function.
Yes. Yeah, the fraction of minimal distance, sure. So in some sense, if you look at these results, it kind of mystifies things rather than clarify things, because we say, what kind of topologies can give rise to these robust entanglement local Hamiltonians? We don't know. They're probably, maybe it's not good that they're too expanding. There was another result that says exactly like that. Maybe not too local and maybe not too random looking, then what is it, right? It needs to have some structure, but maybe not too much structure, because the other end, if you have a local Hamiltonian which just sits on a regular grid, think of just a 3-dimensional grid like cubes, right? If your Hamiltonian just respects that grid, it's very easy to approximate the state. Just run a brute force diagonalization on each block and supply a tensor product of these blocks, right? And disregard anything that crosses between, because like the ratio of envelope to volume is so low, then you wouldn't lose too much in terms of energy. Yeah. This one? No, highly expanding mean like so you take a left subset and you talk about the neighbor set of that. Yeah. Yes, combinatorial. Okay. So that was the end of the quantum part. So that was kind of a bonus, right? You think about quantum, and you may end up in other parts. So the first set of results, and these are all classical now, is motivated by the boson sampling conjecture of Aronson and Arkhipov. Boson sampling essentially means that it kind of feeds into this quantum supremacy race that's going on now. It tells you that maybe we cannot build a universal quantum computer, but maybe we can find interesting distributional problems which are highly intractable, but quantum computers have an easy time solving them. So this was the boson sampling conjecture. And that motivated us to talk about the permanent. I'm going to talk about this in a second. The first result is that the permanent of a random matrix with vanishing mean can approximate it efficiently in quasi-polynomial time. And there was some recent follow-up work.
So the vanishing is important, because 0, that would be what you want, right?
Yes, 0 would be the boson sampling conjecture. What we've shown that if boson sampling conjecture holds, there would be some kind of a sharp phase shift, because like if you just tilt the balance by a bit, something happens. And follow-up work with Bois and Mehraban at approximating the determinant of a well-conditioned Hermitian matrix, or kappa conditioned, can be computed in this space. I'm going to talk about that in a second as well. So these two works kind of emanated from boson sampling. There was another work which Amnon referred to, which is a classical algorithm for matrix spectral analysis with Michael Van Oor, which kind of runs a simulation of quantum phase estimation and uses perturbation theory techniques to get all eigenvalues and eigenvectors of a Hermitian matrix in parallel time and using very few bits for representation. So it's not like the log-squared algorithm, which you need to get exponential precision throughout the computation. You can use only logarithmically many bits.
So can I ask you about the approximation determinant?
Yeah, I'm going to talk about that. But yeah, everything is. So, permanent, approximation of the permanent. Yeah, so this is a massive slide, but this is the rap sheet of the permanent. Essentially, well, the permanent is right. In general, it's it's sharply hard. The best algorithm we know for general case is Reiter formula. but there have been throughout the years some progress. For example, we know that if you have non-negative entries, you can approximate the permanent. But if it remains sharply hard, even if you allow 0, 1, and you require exact computation. You can also talk about average case, which are the bottom 4 here. And for example, if you talk about zero mean Gaussian matrices, then it is hard to compute their permanent exactly on average. And this also holds for finite fields. In this work, what we did was just take the zero mean Gaussian and push it a bit to 1 over polylog log mean. Okay? In that case, we get that exact computation is sharply hard, just as it was before. But now, if you add approximation, you get a quasi-polynomial time algorithm. I was told by Scott that this is, in fact, the switch here is kind of the only example of a counting problem whose complexity collapses under approximation. Or just switch from exact to approx, and complexity falls down.
Counting the number of perfect matchings is exactly the same. No? You do it exactly hard, and if you want to approximate it, you can.
Yeah, maybe.
It's a permanent anyway. So
Permanent, yes.
it's the same.
Yeah, I'm only saying that it's not a new phenomenon.
Yeah, but it's the same. Yeah.
I think it's the same phenomenon in a different dressing. Maybe. Okay. What do you think about that? Okay, so if I try to summarize all that table into just a 2 by 2 matrix, what I get is that the permanent is sharply hard in the worst case for exact computation, and it remains sharply hard for the average case if you require exact computation. If you allow approximation, for the worst case, it's also sharply hard. The question is what happens if you allow both to err on a constant fraction of on inputs and allow approximation error. Does it remain sharply hard or not? And this was kind of the mystery of the permanent. So we want to compute the permanent probably and approximately. Is it hard? Well, so Aronson and Arkhipov use this as the baseline assumption for the boson sampling conjecture. It is sharply hard to approximate the permanent on almost all Gaussian matrices to inverse polynomial precision. And there's a slight thing here which is zero mean, right? So what's the deal with zero mean? So here's the permanent. Now we ask whether the zero mean is essential. Well, yes, right? Because if you take a real ensemble with a very large mean, all entries are going to be positive with high probability, and then you can apply the Jerome-Sinclair-Vigoda algorithm and end it. So when the mean is small, the problem is that you get a lot of interference. So think of this very, very large exponential summation. If not all products are pointing in the same way, you run into a problem where you cannot invoke kind of a Monte Carlo type sampling like they do in JSV. And this was kind of the meta reason that people said maybe this is a quantum thing, right? Because somehow quantum computers have this built-in interference in them. And Scott and Arkhipov showed that, yeah, so you can use a linear optical setup that actually approximates the permanent on these matrices to a high degree of precision. So this is the main result. What we do is define vanished perm, which is just an ensemble of random matrices with variance 1 and mean 1 over log log n. And the problem is to approximate permanent of a matrix from this ensemble. The result one was that this problem still remains sharply hard if you want to compute this exactly. But for computing this to 1 over poly error, multiplicative error is quasi-polynomial for most matrices. Okay, so this holds also for the Gaussian ensemble and also for Bernoulli matrices with a slight bias. It's kind of the same technique. Essentially, again, what we wanted to defeat was the intuition, which was not true in our view, that the permanent computation is hard just because of the interference of signs. Right? Because think about this now, if you have 1 over poly log log n mean, and you look at like a random submatrix, there's a lot of minuses there, right? Like it's approximately half and half. You won't be able to tell unless you look at a very, very large, and then there's a huge interference, and you probably won't be using any counting technique, approximate counting technique, and yet you can have a quasi-polynomial time algorithm. Okay. Oh, yeah. So I'm not sure I'll have time for this because this is the Barvinok technique. So Alexander Barvinok had a beautiful set of techniques which is looking at the permanent as embedding this as an analysis of complex polynomials. And there's a flurry of results that use kind of a variant of his idea. Among them is our result. And there's also, so you can kind of use it to attack any kind of tough combinatorial structure that you want. So we use it on the permanent determinants. People have used it on the Ising partition function, on Hafnians, Pfaffians. There's a lot of a lot of work in that field. So just to summarize the work on the permanent, so it turns out that the Boson sampling conjecture doesn't require zero mean, so it requires only 1/poly n mean. So it's not really zero. So Boson sampling is actually Sharpie hard, the assumption, right? The conjecture is actually true for 1/√n. What we have shown is that if you allow 1/log n mean, you can get a sub-exponential algorithm, which would probably tell you it's not Sharpie hard already, unless it's strongly SETH is false. And you get a quasi-polynomial time algorithm if it's 1/log n. And if you go like way up and you allow √log n, you get the JSV again. So you can kind of plot this here, right? So this means that in the world where boson sampling holds, it is Sharpie hard to do this for 1/√n mean. And we have kind of placed the barrier like somewhat close, right here. So if it's true, there is a sharp transition with respect to the mean of the distribution. So if permanent is hard, it's not because of the interference of signs, it's because of something else. Okay. So I guess, yeah, so I've already said this. So let's talk about determinants for a second. Okay. How much time do I have, by the way? Oh, 7 minutes. Good. Okay. So like the permanent, the determinant is a degree n polynomial in matrix entries. Unlike the permanent, it has a nice geometric interpretation, right? It's the volume of parallelopiped. And it has a linear algebraic interpretation, right? And the complexity neighborhood is completely different, right? We're no longer talking about Sharpie or anything that difficult. It's somehow stranded between NC1 and NC2. And it even has its own class. Okay. So how about approximation? So multiplicative approximation in a general case, it's complete for the class PL, right, which is the log space analog of PP. And if you would be able to approximate the permanent in a general case to inverse polynomial factors, it would in particular imply that L would be equal to NL. That would be like a serious earthquake. I don't know if it's believed to be true. I don't know. Okay, so it turns out that you can show that complexity, the depth complexity, the space complexity is controlled by the conditioning number of a matrix. This is the ratio between the largest and smallest eigenvalues, singular values. This is just a summary, again, like we did for the permanent. This is for the determinant. So let's see some results. For a Hermitian matrix, which is K kappa conditioned, you can approximate the absolute value of the determinant in space which is log n plus log kappa space. This is Amnon's result. So this is quantum space, and it tells you, for example, that if you're talking about a typical matrix, right, the conditioning number would probably polynomial, you get a quantum logarithmic space algorithm for the absolute value of the determinant. Okay, so now if the matrix is diagonally dominant, you can approximate this absolute value in L. This is the result by Mutach. And if it's polyconditioned and stochastic, there's actually a classical BPL algorithm for this by Duron and Amnon. And you can also, this is what we can devise a folklore result, which is that if the matrix is K conditioned, the absolute value of the determinant is approximable in log n log kappa space, going through the inverse and so on. So all of these results, you can see the absolute value of the determinant. What is important here is that the sign is not computable in small space. So this is our result, essentially that if you have a kappa conditioned Hermitian matrix, you can approximate the actual determinant with the sign in depth which is log n log kappa. No, classical. Everything is classical. Yeah, essentially, okay, so this is, maybe I'll just say a few words. Both the result on the permanent and the determinant use the Barvinok technique, which is to write a polynomial, a complex univariate polynomial, which interpolates from an easy to compute thing, say determinant of the identity or determinant of the all ones matrix, to your target thing, determinant of your matrix A or determinant of matrix A. And the game is to try and kind of detour around the roots of that complex polynomial to get from here to there. And you use kind of the Taylor series expansion, and then the root of the analysis is to say, if I'm given a specific ensemble of matrices, say Gaussian matrices with vanishing mean, how do the roots distribute in the complex plane? And do they distribute in a way that I can find a way to kind of do analytic continuation to find my target value? Okay. Last algorithm. This is a parallel stable matrix Eigen decomposition. So we're given a Hermitian matrix, say a Hamiltonian, right? We want to find its eigenvalues and eigenvectors. So let's call an algorithm stable, following Demel and co-authors, if any arithmetic operation can be computed in a presentation which has small bit representation. In other words, I don't want to blow up my registers as I grow with the input size, right? I want to fix my architecture and then run growing inputs. So the problem is that there was no parallel stable algorithm for eigenvalue decomposition. So there are well-known parallel time algorithms for computing eigenvectors and eigenvalues in log squared n time by Sankey, and its complexity is n to the omega plus 2. Omega is the minimal number of operations to compute product of two matrices, but it is unstable. And subsequent work reduced that number to n to the omega plus 1 in log squared n time, but it's still unstable. In other words, as far as we know, if we want to compute a spectral decomposition of a matrix, at some point we need to go through exponential precision. So our theorem was to say there exists an NC2 algorithm. It still runs in log squared n depth, which has the state-of-the-art complexity in terms of multiplication n to the omega plus 1, but it is stable. And the way we do it is, again, to tap into the quantum computer in a way. So we define, everything here is classical. So we define a classical procedure to sample a random eigenvector. So how do we do it? We take our matrix A and we exponentiate it. This is the unitary matrix. Now it becomes a unitary matrix. We can do this very, very quickly. And then we run a single precision phase estimation. I didn't tell you what that is, but it's just kind of a procedure which returns a single eigenvector in a way. So we kind of simulate a quantum computer classically, using as many bits as we need, to get a single eigenvector. Now, the problem becomes, how do you do all eigenvectors in parallel? So what we did was to say, let's run many copies of this procedure on different integer multiples of the matrix A. Okay? So why does that work? We show a technical lemma, which is that it's kind of maybe interesting on its own. It tells you that if you take a matrix A and you bombard it with a Gaussian perturbation, and then you take you map the eigenvalues to the unit circle by taking e to the I power of them, then the integer multiples of these eigenvalues tend to mix quickly. So think of the exponentiated eigenvalues as a point in 0, 1 to the n. It tells you that if you take a large integer power, it mixes quickly. It visits every subcube with probability that is proportional to its volume. It is a low discrepancy sequence in a way. And because it mixes quickly under the Gaussian perturbation to the matrix, we can leverage that property to kind of spit out all the eigenvalues in parallel by running many, many copies of this F. Maybe it was too much of a technical deep dive, but this is kind of the basic idea. And again, this is a completely classical result, which, the core computational, black box was this, the quantum phase estimation. Yeah, thank you.